In the last video, we introduced Gauss's theorem. Let's see if we can put it to use here in this example. So I didn't feel like writing out the entire problem, so I kind of gave you the sketch or the important pieces here. So we have d as described, we have f as given, set up an integral that gives that. All right. Well, again, if we want to use Gauss's theorem, we would need to check our criteria. Okay, so I'm going to just verbally go through these. Do we, okay, so D is the region shown. Okay, so solid, a solid tetrahedron. Okay, so then finally many piecewise smooth. Yep. Closed orientable surfaces. So, or sorry, D is a solid region. The boundary consists of finally many piecewise smooth. Yep. Closed. Yep. Orientable surfaces. Okay. Yep. Okay. And we do need to check that the unit intervals point away from D. But that aside, we we do get that satisfied eventually. So then if we go ahead and set this integral up, okay, we're going to have the triple integral. So if we do this, okay, so we're going to say that the closed surface integral over the boundary of D is vector surface integral, oops, big S, big S, okay, is equal to the triple integral of over D of the del operator dotted with F dV, okay, and now if I figure out D, or the gradient of F, or the del operator dotted with F, what I end up getting is, okay, 2xyz plus 2xyz plus 2xyz. Well, that works out magically. 6xyz. Okay, so then if I look at this, this is going to be, okay, I'm going to leave some room because I need to figure out the bounds, and then 6xyz, okay? And for my order of integration, I'm going to do dz, dy, dx, okay? And we got some practice with this last week, so I think you could take a shot at figuring out the bounds. So pause the video, try that out, and resume when you're ready. Okay, well, hopefully we did that, and if we did, we should have gotten this, 0 to 1 minus x minus y, and then 0 to 1 minus x, and then 0 to 1, okay? And again, you could have chosen a different order. I just happen to choose this. So again, if you evaluate this, you get the vector surface integral over the boundary of D. Okay, great. Now, something more theoretical to consider, but it's actually kind of fun. We can, okay, so suppose D is a region to which Gauss's theorem applies. Great, so we don't have to check all those theorems. And we have G defined as the curl of a vector field, and we know it's C2, okay, so continuous second partial derivatives. Show that that is zero using Gauss's theorem, and then eventually Stokes's theorem, okay? Well, if we look at Gauss's theorem, remember that integrals aside, we're going to want to compute, oops, I want this one. We're going to want to compute the del operator dotted with G, right? Well, this is really the del operator dotted with, and then the del operator cross F, and now we have to remember some theorems, and it says that if we do the divergence with the curl, the composition of the two in order, we end up with 0. Ah, great. So really when we do, oops, when we look at the closed vector surface integral over the boundary of g dot ds, this is the same as the triple integral over over the divergence, okay, and then this is just 0. Great, one of them done. Now with Stokes's theorem, this is a little bit more interesting. This was looking at a double integral over the boundary of our region, and then we were looking at this, the curl of the vector field, okay, dot ds, and then Stokes' theorem was equating that down to a vector line integral. And when we did this, then this was going to be the closed integral over the boundary of the boundary. So the boundary of the boundary of D of G dot ds. Okay, but now if we know that the boundary, we know that this is a closed surface. So what's the boundary of a closed surface? Well, the boundary of a boundary if the surface is closed is just 0, so actually the empty set. So then we're taking the integral over an empty set, 0, right? So a nice little application that might come in useful.